The alkali earth metals, which include beryllium, magnesium, calcium, strontium, barium, and radium, are found in group 2 of the periodic table. They all have 2 valence electrons. The alkali earth metals are not found as pure elements in nature, only in compounds. These elements, with the exception of beryllium, are known as alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the Earth's crust. The most abundant elements in group 2 are calcium and magnesium. They are the 5th and 6th most abundant elements in the Earth's crust. The other group 2 metals are significantly rarer in nature. Oxide compounds of group 2 elements are found in the Earth's crust. The alkali earth metals have similar properties because of their related electron configurations. Since they all have 2 valence electrons, they form cations with a charge of +2. Shown here are the electron configurations of 4 alkali earth metals. Notice how they all end as S2, showing those 2 valence electrons. The similarities in the electron configurations are even more apparent when written in noble gas notation. They all end as Ns2, where N is the highest occupied electron energy level. Because of their 2 valence electrons, all the group 2 metals form cations with +2 charges. By losing the 2 outermost electrons, they form cations that are isoelectronic with the nearest noble gas. Let's go on and review the periodic trends as they relate to the alkali earth metals. In general, atomic radius decreases from left to right in a period. In groups moving from left to right, outermost electrons enter into the same electronic shell. Therefore, size does not increase. Moreover, outermost shell is held more tightly by the increasing nuclear charge. Thus, we see that an alkaline earth metal has a smaller atomic radius than the group 1 metal in the same period. As shown in the graphic, atomic radius increases down a column because the electrons enter into new electronic shell and inner shells act as screens for outer electrons. Therefore, outermost shell is held less tightly by the nuclear charge. This pattern holds for the group 2 metals as well. Let's consider the ionic size trends. Cations are smaller than their parent atoms due to increased nuclear charge. As mentioned earlier, the group 2 metals typically form ions with a +2 charge. As shown in the graphic, the group 2 cations that form are significantly smaller than the neutral metal atoms. Recall that ionization energy is the energy required to remove an electron from a neutral, isolated atom. A typical equation representing this change is shown. In general, ionization energy increases from left to right across a period. The outermost electrons are held more tightly as the nuclear charge increases. In accordance with this trend, the alkaline earth metals have higher first ionization energies than the alkaline metals. The second ionization energy is the energy required to remove the second electron. Once the first electron has been removed, as indicated in the equation here, Generally, second ionization energies are higher than first ionization energies. One interesting fact you should know: the second ionization energies for the group 2 metals, that is, alkaline earth metals, are lower than the second ionization energies for the group 1 metals, that is, alkali metals. This is because losing one electron for a group 1 metal gives it a noble gas-like electron configuration, and losing another electron from these cations becomes significantly less favorable. The alkali earth metals have relatively low ionization energies. However, reflecting their high tendency to lose electrons, ionization energies for the group 2 metals decrease down a column. So, we can describe the alkali earth metals as electropositive, and they become more electropositive down the column. Hydration enthalpy is defined as the amount of energy released when 1 mole of an ion is dissolved in a large quantity of water. As ionic size increases, hydration enthalpy decreases. Therefore, we observe a decrease in hydration enthalpy from beryllium through barium. The group 2 metal ions have larger hydration enthalpies than the corresponding group 1 metal ions. Many salts of the group 2 metals are found as extensively hydrated salts. For example, magnesium chloride and calcium chloride both exist as hexahydrates. Neither potassium chloride nor sodium chloride is found as a hydrate. However, let's discuss the physical properties of the group 2 metals. The alkali earth metals are silvery white, lustrous or shiny solids, although beryllium and magnesium may have a greyish cast to them. They are relatively soft metals, though harder than the alkali metals. Like all metals, they are good conductors of heat and electricity. The group 2 metals have higher boiling points than the group 1 metals due to their smaller atomic radii. Similarly, the group 2 metals have higher melting points than the group 1 metals in the same period, although the trend is not systematic. Flame tests are a simple, qualitative way to test for the presence of metals. By holding a sample of a metal salt in the flame and observing the change in the color. The heat of the flame excites the electrons to a higher energy level, and then the electrons emit light as they return to the ground state. Calcium salts produce a characteristic brick red flame. Strontium salts can be recognized by the crimson flame that results. Strontium salts are used to make fireworks that emit red light. Barium gives an apple green color to the flame. Why don't magnesium and beryllium produce colored flames? The electrons are held tightly by the nuclei in these elements, and so the flames do not excite them to higher energy levels. Magnesium, in fact, will ignite in the flame and react with oxygen, giving off an intense white light. Now we should discuss various chemical properties of the alkaline earth metals. In general, the alkaline earth metals are less reactive than the alkali metals. The group 2 metals form a variety of different types of compounds. Our focus is on the oxides, hydroxides, halides, carbonates, sulfates, and nitrates. We'll discuss each of these in turn. Magnesium and beryllium do not react with water because both the metals form an oxide layer on their surfaces. Calcium, strontium, and barium all react with water at normal temperature to form hydroxides. The reaction of calcium with water is shown here. These hydroxides have low solubility in water and are less basic than the group 1 metal hydroxides. In general, for the group 2 metal hydroxides, as the atomic number of the metal increases, the solubility, thermal stability, and basic character all increase. Beryllium hydroxide, unlike the other group 2 metal hydroxides, is amphoteric. It can act as both an acid and as a base. In the first reaction, beryllium hydroxide acts as a Lewis acid by accepting electron pairs from hydroxide ions. In the second reaction, beryllium hydroxide acts as a base with hydrochloric acid. Why do the group 2 metal hydroxides become more soluble down the group? Recall that metal cations increase in radius down a column. As internuclear distance increases, lattice energy decreases. So, less energy is required to separate the ions. The hydration enthalpy, however, decreases less dramatically. The net result is that the salts are more soluble in water. Beryllium and magnesium do not react with oxygen at normal temperature due to the formation of an oxide film on their surface. When burned in oxygen, the group 2 metals form metal oxides. For example, burning calcium in the presence of oxygen forms calcium oxide. Magnesium and beryllium, when ignited, will react vigorously in air, releasing a bright light. Both the oxide and the nitride will form when reacting in air, as shown here in the reactions for magnesium. Calcium, strontium, and barium also react in air to form oxides and nitrides. Beryllium oxide is essentially covalent in character. It is an amphoteric oxide, meaning it can act both as an acid and as a base. The other group 2 metal oxides are essentially ionic substances, and the basic nature of oxides increases from magnesium to barium. With the exception of beryllium oxide, the group 2 metal oxides are basic anhydrides. This means that they react with water to form metal hydroxides. All the group 2 metals can react with halogens, forming halide compounds. These reactions usually occur at high temperatures. For example, calcium fluoride forms when calcium metal reacts with fluorine gas. a sample of fluorite, a naturally occurring mineral of calcium fluoride, is shown in the photograph. The best synthetic route for preparing beryllium fluoride is to heat ammonium beryllium fluoride until it decomposes, as shown in the equation here. Beryllium chloride can be formed by reacting beryllium oxide with chlorine gas in the presence of carbon. Carbon monoxide is a byproduct of this reaction. The halide salts of the alkaline earth metals are essentially ionic in character, with the exception of the halides of beryllium. The beryllium halides are primarily covalent and thus are soluble in organic solvents. In the solid state, beryllium chloride has a chain structure. However, in the vapor phase, beryllium chloride forms a dimer. These dimers dissociate into monomers at very high temperatures. The halides of the group 2 elements are often found as hydrates, but these salts are complexed with fewer water molecules down the column. Thus, magnesium chloride is an octahydrate, whereas barium chloride is found as a dihydrate salt. These salts can be dehydrated upon heating, leaving anhydrous salts. It should be noted that beryllium and magnesium salts will undergo hydrolysis upon heating, though, in general, the fluorides tend to be less soluble than the chlorides because of the higher lattice energies associated with the fluoride salts. All of the group 2 metals, with the exception of beryllium, react with hydrogen to form metal hydrides. The reaction involving the formation of calcium hydride is given here. Beryllium hydride can be produced by reacting beryllium chloride with lithium aluminium hydride. The group 2 metals react with acids in a single replacement reaction, releasing hydrogen gas as a product. As a family, the alkaline earth metals have large negative reduction potentials. This feature reflects the strong tendency of the metals to lose electrons, otherwise known as oxidation. Since oxidation cannot occur without reduction, they can be considered good reducing agents. Beryllium has a lower reduction potential than the other group 2 metals because its cation is smaller and has a larger atomization energy. In liquid ammonia, the group 2 metals dissolve to form solutions with a deep blue-black color. Ammoniate salts of the general formula shown here can be recovered from these solutions. The carbonates of the group 2 metals are insoluble. They can be prepared by reacting soluble carbonate salts, such as group 1 or ammonium carbonates, with soluble salts of the group 2 metals. One such reaction is shown here. A photograph of the mineral calcite, a naturally occurring form of calcium carbonate, is shown here. The group 2 metal carbonates decompose upon heating to form the oxide and carbon dioxide, as shown for calcium carbonate here. The White Cliffs of Dover consist primarily of calcium carbonate. The thermal stability of calcium carbonate increases as the metal cation increases in size. Beryllium carbonate is unstable and must be kept in a carbon dioxide atmosphere. The sulfate salts of the group 2 metals are white solids that are heat stable. Beryllium sulfate and magnesium sulfate are water soluble. But the solubility of this class of compounds decreases down the column. This is because beryllium and magnesium ions have higher hydration enthalpies than the other metals in the group. The group 2 metal nitrates can be prepared by dissolving the carbonates in dilute nitric acid. This class of compounds repeats the pattern of the decreasing tendency to form hydrates down the column. For example, magnesium nitrate is found as a hexahydrate, but barium nitrate is anhydrous. When heated, all the group 2 metal nitrates decompose to form oxides, as shown in the equation for the decomposition of calcium nitrate. The alkali earth metals are used for a variety of purposes. We'll wrap up this module with an overview of the uses of these metals. Beryllium is used in many industries. It is used to prepare several alloys. A copper beryllium alloy is used to manufacture high-strength springs. Metallic beryllium is used for the windows of X-ray tubes. The inhalation of beryllium dust, vapor, or its compounds can cause berylliosis, a serious form of mental poisoning. Magnesium is also used to prepare alloys. A magnesium-aluminium alloy is used in the construction of airplanes. Magnesium metal is used in flash powders and flash bulbs for cameras. Milk of magnesia, a suspension of magnesium hydroxide, is used as an antacid. Magnesium carbonate is used as an ingredient in toothpaste. Calcium is used in the extraction of metals from oxides when they are too difficult to reduce with carbon. Calcium, along with barium, has been used to remove air from vacuum tubes. The radioactive salts of radium are used in the treatment of cancer. In certain respects, beryllium does not behave like the other group 2 metals. In particular, the compounds of beryllium have a significant degree of covalent character and are easily hydrolyzed. This is due to the exceptionally small atomic and ionic radii observed for beryllium, as well as its high ionization energy and electronegativity compared to the other group 2 metals. Beryllium can achieve a maximum coordination number of 4. This is because there are a maximum of 4 orbitals in beryllium's outermost energy level, namely the 2s and 2p orbitals. The other group 2 metals can utilize the d orbitals to have a coordination number of 6. Beryllium oxide and beryllium hydroxide are amphoteric substances, meaning that they can act as both acids and bases. For example, the first reaction shows beryllium hydroxide acting as a base, neutralizing sulfuric acid. The second reaction shows beryllium hydroxide acting as an acid to form the complex ion berylate. In several ways, beryllium behaves more like aluminium than the other group 2 elements. It's worth being familiar with the details of this diagonal relationship. First, the beryllium ion and aluminium ion have similar charge to radius ratios as shown here. Neither beryllium nor aluminium reacts readily with acids due to the oxide film that both the metals exhibit on their surface. The hydroxides of both the metals dissolve in solutions of excess hydroxide to form complex ions. In the vapor phase, both beryllium chloride and aluminium chloride form chloride-bridged structures. Both the chlorides are soluble in organic solvents, reflecting their essentially covalent character. Both the chlorides are strong Lewis acids, acting as electron pair acceptors in chemical reactions, as shown in the reaction given here. Both the chlorides are used as catalyst in the Friedel-Crafts reaction shown here. Both beryllium ions and aluminium ions form complex ions. Next, we will consider some important compounds of calcium. Calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. Calcium oxide, which has the chemical formula CaO, is commonly known as quicklime. Calcium oxide is a white, amorphous solid with a melting point of 2870 Kelvin. To prepare calcium oxide on an industrial scale, limestone or CaCO3 is heated in a rotary kiln at 1070 to 1270 Kelvin. At these conditions, calcium carbonate decomposes to form calcium oxide and carbon dioxide. The carbon dioxide is removed continuously to drive the equilibrium to the products. Quicklime absorbs carbon dioxide and moisture from the air, as shown in these reactions. When carbon dioxide is absorbed, calcium carbonate is the product. Slaking of lime, shown in the second reaction, refers to the process in which, when a limited amount of water is added to a lump of lime, it breaks up and results in the formation of a suspension of slaked lime along with the liberation of heat. This reaction also shows that calcium oxide is a basic anhydride, since its reaction with water forms calcium hydroxide, which is alkaline. Calcium oxide is a basic oxide, and thus can combine with acidic oxides at high temperature. For example, Reactions with silicon dioxide and phosphorus pentoxide are given here. Calcium oxide has a number of industrial uses. It is necessary for the manufacture of cement and is the cheapest form of alkali. It is used to produce sodium carbonate from sodium hydroxide, also known as caustic soda. It is used in the purification of sugar and in the manufacture of various dyes. Calcium hydroxide. Another important compound of calcium is commonly known as slaked lime. It is a white, amorphous powder that can be prepared by adding water to calcium oxide. Calcium hydroxide is only sparingly soluble in water. Aqueous solutions of calcium hydroxide is commonly called lime water. Milk of lime is the common name for suspension of calcium hydroxide in water. Lime water provides a simple test for the presence of carbon dioxide. Lime water turns milky when carbon dioxide is passed into it. A precipitate of calcium carbonate forms in this reaction, as shown here. If more carbon dioxide is passed into the above solution, the precipitate dissolves and forms calcium hydrogen carbonate. Milk of lime, a suspension of calcium hydroxide in water, reacts with chlorine gas to form calcium hypochlorite, the main component of bleaching powder. Hypochlorite ion is a good oxidizing agent. Calcium hydroxide is an important industrial chemical. It is used in the preparation of mortar and to make whitewash. It is necessary for making glass as well as for the tanning of leather. As was just discussed, it is used in the preparation of bleaching powder. It is also used in the purification of sugar. Calcium carbonate occurs naturally in several forms, including limestone, chalk, and marble. In its pure state, it is a white, fluffy powder that is nearly insoluble in water. Upon heating, it decomposes to form calcium oxide and carbon dioxide. Calcium carbonate can be formed in two ways. The first process involves passing carbon dioxide through slaked lime, as shown here. Alternatively, sodium carbonate reacts with calcium chloride to form calcium carbonate and sodium chloride. This is shown here. Calcium carbonate is used for a variety of purposes. It is well known as a building material. It is necessary in the manufacture of quicklime. It is used industrially as a flux in extracting metals from ores and in the manufacture of high-quality paper. It is also used as an antacid. Calcium carbonate is an ingredient in toothpaste and chewing gum and is used as a filler in cosmetics. Plaster of Paris is a hemihydrate of calcium sulfate. Plaster of Paris is formed when gypsum or calcium sulfate dihydrate is heated to 393 Kelvin. The decomposition reaction is shown here. If gypsum is heated above 393 Kelvin, anhydrous calcium sulfate or dead burnt plaster will be the product. When water is added to plaster of Paris, it forms a plastic, malleable mass that hardens in 5 to 15 minutes. Plaster of Paris is used in the building industry. In medicine, it is also used to prepare casts to set bone fractures. It has applications in dentistry too. Besides, plaster of Paris is used for ornamental work, such as the ceiling medallion shown here, as well as statues. Cement, or Portland cement as it is often called, is another important compound of calcium. The raw materials for making cement are limestone and clay. The composition of cement is not fixed. Portland cement typically contains 50 to 60% of calcium oxide and 20 to 25% silicon dioxide as its main components. Cement also contains 5 to 10% aluminium oxide, 2 to 3% magnesium oxide, 1 to 2% iron 3 oxide, and 1 to 2% sulfur trioxide. In good quality cement, the ratio of silica or silicon dioxide to alumina or aluminium oxide is between 2.5 and 4. The ratio of lime or calcium oxide to the total oxides of silicon, aluminium and iron should be as close to 2 as possible. Cement clinker is formed when clay and lime are strongly heated. They fuse together to form cement clinker, shown in the photograph. To form cement, 2 to 3% gypsum by mass is added to the cement clinker. This mixture is then ground to make cement. Ingredients that make up the bulk of Portland cement include dicalcium silicate, making up 26%, tricalcium silicate, contributing 51%, and tricalcium aluminate, contributing 11%. Cement sets when it is mixed with water to form a hard mass. The molecules of the components get rearranged and hydrated. The presence of gypsum slows down the setting process so that it gets very hard. Cement is used to make concrete and reinforced concrete. It is used in plastering as well. It is best known for its use in the construction of bridges, dams, and buildings of all sorts. Both magnesium and calcium play important roles in biological systems. An adult human body contains 25 grams of magnesium and 1,200 grams of calcium. Compare this with only 5 grams of iron and 0.06 gram of copper. Let's go into these important functions in more detail. Phosphoryl transfer enzymes, which use ATP in phosphate transfer, use a magnesium ion as a cofactor for enzyme function. An illustration of one such enzyme is shown here, with the magnesium ion shown in green. Chlorophyll is the main pigment in plants that absorbs light for photosynthesis. The porphyrin ring in chlorophyll contains magnesium. Bones and teeth contain about 99% of the calcium in the human body. Bone, which is alive, with a complex structure, is continuously being solubilized and redeposited in the body. Approximately 100 milligrams of calcium are dissolved in 1 liter of plasma. This concentration is regulated by the action of two hormones, calcitonin and parathyroid hormone. Calcium ions play an essential role in muscle contraction. A diagram of the sliding filament theory of muscle contraction is shown here. Calcium ions also play an important role in blood coagulation. Calcium ions are essential for the transmission of signals between nerve cells. Calcium ions are important for cell signaling and for various physiological processes. Calcium channels regulate the transportation of calcium ions across cell membranes.